In this video, we're going to determine the empirical formula of an unknown when we don't have all of the molecular mass, when we don't have all of the mass percent info to start with. In this case, a sample of 2.05 grams of this unknown containing hydrogen, carbon, oxygen, and mercury was sent to elemental analysis, and it came back with 15.1% carbon, 1.9% hydrogen, and 62.9% mercury. No oxygen data was given. This is actually often the case. Most of the time when we obtain these percentages from a lab, they do it by burning the material, which means they add extra oxygen from outside. If they were to try to add up all the oxygen, they'd have more oxygen that wasn't from the molecule. It would have come from outside sources. And so actually getting the mass percent of oxygen directly is rather difficult. However, if we are fairly certain that our compound is composed of nothing but hydrogen, carbon, oxygen, and mercury, then we can just do a difference from 100%. Remember that all of your things must add up to the total. So there should be 100% total. I know that 15.1% of it comes from carbon, 1.90% comes from hydrogen, and 62.9% comes from the mercury. Well, whatever's left must be the amount of oxygen. We'll find that that's 20.1, so oxygen should be 20.1%. Now, this isn't a direct measurement. It's assumed through the difference. There could always be something wildly wrong with your molecule or your formula. Calculating out what oxygen should be based on what's remaining to add up to 100% isn't great, especially if you had a contaminant. Maybe only 1.95 grams was your sample, and maybe a little bit of paper, maybe 0.1 grams of paper just got in there. In lab, you tend to scratch filter paper to scrape things off. Small fibers can get in. It's not a perfect method, but it does get us what is likely in range of the actual percent of oxygen as long as we performed this creation of our material correctly. Once we have that then allows us to find the empirical formula. We wouldn't have been able to find it for oxygen if we didn't know how many moles of oxygen we had, but we can presume the moles of oxygen based on the remaining percentages in this molecule that should have come from oxygen. Well, for this, I need to calculate out some masses of each thing so I can then find moles. I could take my gram of sample and find out what 15.1% of 2 grams is, but this actually isn't necessary. I don't need to know the actual weight of carbon in my sample to find the empirical formula. Whatever weight of sample, it's always going to be 15.1%, so I can just pretend 100 grams, because then my percentage is just my grams. 15.1 grams of carbon. It just saves me one calculation. Instead of 2.05 times 0.151 to find the real grams of carbon and then turn them into moles, I can just straight up use the percentage if I assume a 100 gram sample would also have 15.1%. And so I save myself one calculation for each element. It's 12.01 grams of carbon in 1 mole. For 1.26 mole of carbon. If I do that for hydrogen, 1.90 grams of hydrogen at 1.008 grams in 1 mole. For 1.89 mole of hydrogen. I can do that for my mercury, 62.9 grams of mercury at 200.6 grams of mercury in 1 mole of mercury. For 0.314 mole of mercury, and the presumed amount for oxygen of 20.1 grams of oxygen, and there's 16 grams in 1 mole, for 1.26 mole of oxygen. Well, right away our moles of oxygen kind of match our moles of carbon. That's a good thing. We want whole number ratios, and if they happen to be the same number, then same number of moles makes sense. So it seems like our 20.1% of oxygen is probably reasonable. It's matching up to one of our other things. Carbon, hydrogen, oxygen, mercury, 1.26, 1.89, Oxygen's 1.26, mercury is 0.314. The lowest is the mercury, 0.314, which means we will find that our carbon comes out 4.01, our hydrogen comes out 6.02, oxygen 4.01, and mercury 1. So C4H6O4Hg. This is our empirical formula. It could be a multiple of this. We don't have a molecular mass to compare, so we don't know if it's maybe twice or 3 times or 20 times this. I will tell you just when I developed it, this is mercury diacetate. And so it happens that this time the empirical formula also matches the molecular formula. But that is not something we can know for certain unless you're the person who wrote the problem or you have a molecular mass from one of the various methods that can give us molecular mass, such as mass spectrometry. But here's our empirical formula, C4H6O4Hg.